Have you ever been stuck in a massive online queue for, say, concert tickets, and just wondered how the website doesn't completely melt down? Well, that's not luck. It's actually a set of incredibly clever engineering principles. Today, we're going to pull back the curtain and look at the 5 core ideas that allow the biggest apps in the world to handle millions of us all at the exact same time.
So, here's our game plan. First up, we'll dig into why this whole thing is such a monumental challenge to begin with. Then we'll start opening up the toolkit. How to get answers instantly, how to build systems that basically never break, and the secrets behind those location-aware services. And to wrap it all up, we'll see exactly how the biggest companies in the world put all these pieces together. All right, let's start with the core problem, right? Modern applications, the ones we use every day, face these almost impossible demands for speed, for scale, and for being available all the time. Now try to wrap your head around this for a second. Every single minute, the world generates enough new data to fill millions of bucks. That's every photo you upload, every message you send, every search you make. And that data isn't just getting stored away in some dusty archive. It has to be processed and ready to be served right back to you in the blink of an eye. That's the mind-boggling scale of the challenge we're talking about. And these are the fundamental hurdles that every large-scale system has to clear. The amount of data never ever stops growing. Users who are just reading data have totally different needs than the systems writing new data. And here's a big one: networks will always fail. It's not a question of if, but when. On top of all that, you have to be able to update your app's foundation without ever taking it offline. Solving for all of this, well, that's the name of the game. So how in the world do you stay fast under all that pressure? Let's get into the first set of tools in our toolkit, all of which are designed for just blistering performance. You know, this is such a great question. Imagine going to a massive library to look for a book that isn't even there. You'd waste a ton of time, right? In the digital world, that wasted time means slow apps and really high costs. So, how do we stop that from happening? Enter the Bloom filter. You can think of it like a super fast, maybe slightly forgetful bouncer for your database. It stands right at the door and can instantly tell you if someone is definitely not on the guest list, saving you the hassle of doing a full search inside. And here's the secret to its speed. Instead of doing a full, costly search, it just checks a simple digital fingerprint. If that fingerprint doesn't match, it basically slams the door and says, nope, not here, and the database doesn't have to do any work at all. Now, if the fingerprint does match, it says, okay, this person might be here. Go ahead and double check inside. The absolutely crucial part is that it will never tell you something isn't there when it actually is. It only makes mistakes in the other direction. Speed is one thing, but what about just staying online? Let's move to our next big challenge and see how engineers build systems that can handle failures and evolve over time, all without ever shutting down. I mean, this is the nightmare scenario, isn't it? For any global service, putting up a down for maintenance sign just isn't an option. So if the very heart of your system, the primary database, fails, you better have a backup plan that's already up and running. And that plan is called replication. It's kind of like having identical twins running your store. If one of them is busy with a customer or needs to take a break, the other one can step in seamlessly and nobody even notices. By having multiple up-to-date copies of your data, you make sure that a single point of failure doesn't take down your entire service. And right here is where engineers have to make a really key decision. With synchronous replication, you wait for all the copies to confirm they have the new data. It's much safer, but it's also slower. With asynchronous, you just move on immediately and trust the copies to catch up on their own. It's way faster, but you do run a tiny risk of data lag if a failure happens at just the wrong second.
Being unbreakable also means you have to be able to change. This expand, migrate, contract pattern is this beautiful strategy engineers use to change the very bones of the database while the app is still running. First, you expand by adding the new structure. Then you migrate the application and the data over to it. And only when everything is safely moved over do you contract by removing the old parts. It's this elegant dance that means users never even realize a major upgrade is happening under the hood.
All right, let's totally shift gears for a minute. We've talked about speed and reliability, but what about the magic behind apps that just know where you are? Let's dive into the unique challenge of geospatial data. This right here is the secret sauce. A normal database is awesome at finding text or numbers, but it's just terrible at answering questions based on physical space. Geospatial databases, on the other hand, are built from the ground up to understand latitude and longitude, which makes answering location-based questions incredibly fast. And you use these all the time without even realizing it. When you open a map to find a coffee shop, or a ride-sharing app shows you all the nearby cars, or a food delivery app checks if it can deliver to your address, that is a geospatial database working its magic, performing really complex distance calculations in milliseconds.
So we've seen all these individual tools, but the real power, the way big tech operates at a truly planetary scale, is by combining them into one cohesive system.
And this is so key. There is no perfect tool. Engineering is all about making trade-offs. Bloom filters are tiny and fast, but can have false positives. Replication gives you amazing availability, but you might have some lag. Even NoSQL databases, which are built for massive scale, can be less flexible for certain queries. The best architects have to choose the right tool and accept the right trade-off for every single job. So let's see how this all comes together in the real world. Google uses Bloom filters to speed up its massive storage systems, and of course, geospatial databases for Google Maps. Amazon builds its legendary availability on a foundation of replication. And ride-sharing apps, they're a perfect symphony of these tools. A geospatial database finds you a nearby driver, while replication makes sure the service works whether you're in Tokyo or Toronto. This quote right here really captures the entire philosophy. A Bloom filter stops useless requests from ever bothering the database. Replicas take all the read pressure off the primary database. It's a cascading system where each component protects the one downstream, allowing the whole system to handle an absolutely incredible amount of load. So the next time you search for something, book a ride, or just scroll through your social media feed, just take a second to think about the incredible architecture that's humming away behind the scenes. Which of these tools are working together to make that seamless experience possible? That's the invisible engineering that powers our entire digital world.